All right, let's jump right in. Today, we're tackling a huge topic, the brain versus the machine. We all know they both think in their own way, but how they think? Well, that's where things couldn't be more different, and it's where our story begins.
So, here's the game plan. We're going to start with the brain and why it's more like a living ecosystem than a piece of hardware. Then, we'll pivot to the computer, this digital machine we built. We'll put them head-to-head, look at the next frontier of brain-inspired tech, and finally, talk about the biggest challenge of all, us.
So, let's kick things off with the big one, the question that really sits at the heart of all of this. Is your brain just a wet, biological computer? It's a comparison we hear all the time, but I have a feeling that by the end of this, you'll see it in a whole new light.
Okay, so first up, the human brain. And I want you to try something. For a minute, just forget everything you think you know about it being a machine. To really get it, we have to appreciate the sheer, mind-bending scale of what nature has created. It all starts with this number, an absolutely staggering number. We're talking about 86 billion neurons. To put that in perspective, that's more than 10 times the number of people on the entire planet, all buzzing away inside your head. But you know, as crazy as that neuron count is, it's not even the whole story. Not by a long shot. Because each of those neurons connects to thousands of others. And that gives us an estimated 10 quadrillion synapses. This isn't just a big network. It's practically a universe of connections. And this, right here, gets to the core of it. A system this dense and interconnected, it wasn't engineered, it wasn't built on a factory line. It behaves less like a predictable machine and, well, way more like a wild, chaotic, and beautifully complex natural ecosystem.
So how does this crazy ecosystem actually work? Well, for starters, it's asynchronous. Unlike a computer that ticks away with a steady clock, neurons only fire when they have something to say. It's all happening at once, what we call massive parallel processing. And here's the magic trick. It's constantly changing, rewiring itself. That's called plasticity, and it's literally how you learn. Oh, and memory and processing? They're not in different buildings. They're completely intertwined. The system can even patch itself up when it gets damaged.
All right, now let's completely switch gears. If the brain is this organic, evolving ecosystem, the computer, well, that's a whole different beast. It's a precision-engineered machine, built from the ground up on very, very rigid rules. At the very core of every modern computer is this idea, digital processing. Everything, and I mean everything, gets boiled down to simple, clean, unambiguous ones and zeros. It's incredibly reliable, super precise, and it all marches to the beat of a central clock, keeping everything perfectly in sync. And this right here is probably the single biggest design difference. In any computer you've ever used, the part that does the thinking, the CPU, is physically separate from the part that remembers stuff, the RAM. So to get anything done, data has to be constantly shuttled back and forth between these two spots. And all that shuttling back and forth, it creates a massive traffic jam. It's a fundamental bottleneck that engineers call the memory wall. It doesn't matter how unbelievably fast your processor gets if it's constantly just sitting there, waiting for data to arrive from memory. It's a limitation baked right into the architecture. Okay, so we've looked at the living ecosystem of the brain and the rigid machine of the computer. Now, let's put them side by side. This is where the differences really pop. Just look at this breakdown. The brain, integrated memory and processing. The computer, separated. The brain is these rich, messy analog and chemical signals. The computer, clean, perfect, digital ones and zeros. The brain is this massively parallel, asynchronous free-for-all, while the computer is a step-by-step, synchronous assembly line. And maybe most importantly, the brain is alive. It adapts, it changes, it heals. A computer is fixed and rigid. So here's the big takeaway. They don't just work differently. This isn't a case of two different models of cars. They are fundamentally, from the ground up, different kinds of systems. And this is where that old brain is a computer metaphor just completely breaks down. And because of this massive divide, scientists are now on this incredible quest to build a totally new kind of machine, one that actually learns from the brain's playbook. The name for this field is neuromorphic computing. And the whole idea isn't just about making computers faster. No, it's much bigger than that. It's about rethinking them from the ground up, using the brain's own brilliant architecture as the blueprint. So how are they even trying to do this? Well, it involves creating new kinds of chips, neuromorphic chips, that have artificial neurons and synapses built right in. They're developing what's called in-memory computing,
to finally tear down that memory wall. And they're experimenting with these wild hybrid systems that try to get the best of both worlds, the efficiency of analog with the precision of digital.
But make no mistake, this is incredibly hard stuff. You're trying to smash together two different worlds of chip design. You have to figure out how to control errors in these noisy analog signals. And you literally have to invent brand new ways to program a machine that doesn't think in a straight line. The challenges are just massive.
And that brings us to our final hurdle. And honestly, it might be the biggest one of all. Because the challenge isn't just about the technology, it's about us.
See, you've got all those technical barriers we just talked about, but then there's something else, the limits of our own human perception. Our senses, our sight and hearing, they only capture a tiny, tiny slice of what's actually happening inside a living brain. We simply can't see the full mind-boggling complexity directly. What this really means is that to understand the brain well enough to build one, we need more than just better circuit boards. We need tools that let us see beyond our own senses. We need AI, complex mathematical models, and new ways of imaging to act as our translators, to show us the universe that our own eyes can't perceive.
And this is the thought I want to leave you with. Let's say we do it. We overcome every single one of these challenges. We actually build a true, functioning artificial brain. The question then becomes, will we have the tools, or even the mental capacity, to truly understand what it's thinking, to comprehend its inner world? That's the real frontier.